Presenting for the classmates that are not here today so that they understand what's happening. There we go. It doesn't have to be great. Anyway, so at this point, the acceleration, right? It accelerates the direction you push or pull it. So in the case of the car, right, when we went down the ramp, the fact that you put it on the ramp and gravity took it, which direction? Downward, right? Yeah. And so as you saw, as the direction, right, that the push or the pull, in this case the push or the pull was gravity, took the car down the ramp. And so the larger the mass of the object, the higher the acceleration that you would have seen, okay? Now, of course, you only did Hot Wheels cars. Oh, what is going on? So at that point, the acceleration was minimal. So if you have a large force, stay with me, right? If you have a large force, you're going to have large acceleration. Whereas if you have a smaller force, you're going to have small acceleration. Okay? You guys should understand this. If you've got two vehicles going down a hill, right? Say you've got a semi versus a car, and the semi and the car start out at the same force, with the same force, who's going to have the larger acceleration? The semi. Why? It's a lot heavier, right? You have a lot more mass with the semi. So that's when you have to watch out, because sometimes the semi, the brakes go out, right? Correct? Okay, and you'll see down big hills like in mountain areas like Tennessee, you'll see roads off to the side that they can just take those roads if their brakes go out, right? And then the road takes them uphill to counteract that gravity and the acceleration. So if you push twice as hard, it accelerates twice as much, okay? So using the same amount of force, if we have a large object and a small object, using the same force to push the object, you got to think which one's going to go faster and farther, okay? Is it with the large mass or the small mass? Okay. You probably think of this, for example, if you're playing a game, or maybe you're like wrestling with your brother, right? You've got two different siblings, and you know, wrestling your brother, and all of a sudden you're the same mass and you're using the same force, and you're wrestling, and the acceleration is just fine, right? You guys can wrestle between each other, but what happens when you go to wrestle your five-year-old nephew with the same force? Not good, right? You're going to push him down. He's going to get hurt because you've got him going at such a larger acceleration using that same force because he's such a smaller mass, right? Thinking about the smaller mass. So Newton's second law states the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. So here's the equation you're going to be using for tomorrow's homework, all right? Not today's homework, tomorrow's homework. Here's the equation, force equals mass times acceleration. You should have heard this one already. This is one of Newton's one of his most famous equations, okay? Force equals mass times his acceleration. So, for example, if we know the force that is being exerted on the object and we know the mass, we can calculate the acceleration of that object, okay? If we know the acceleration and the mass, we can figure out how many newtons of force are being calculated. All right, and that'll be in your problem set tomorrow for homework. So just as an example, thinking about the bigger the object, the harder they fall, right? Thinking about the larger the mass, the larger the force, right? And force is calculated in newtons, which is N. The mass should be in kilograms. Okay, always calculate it. So if we calculate in pounds here, we do have to convert from pounds to kilograms, which you can use the internet for that. That's pretty easy, okay? Finding those pounds to kilograms conversions. Like I said, we're the only ones that use pounds. All the other countries use grams and kilograms. So that's an easy conversion you can do on the internet. And then, of course, the acceleration, you know, is meters per second squared already. We've already done acceleration calculations, and that's easy to find. Right? And so you can calculate it, that acceleration, calculate the force. So when we have this, right, speeding up is a positive, slowing down is negative, also called deacceleration. And we've already done the acceleration equations, right? So when we're looking at Newton's second law, here we go. What helps you remember Newton's second law? So there's your meme board. Go ahead, write it in, find a meme, find something that helps you remember Newton's second law. Remember, everybody needs to post one. That's supposed to be a fat zombie? Is that what's happening? It looks like my Uncle Sonny. I used to have a great Uncle Sonny that looked like that. Carter, Brian, Casey, Sophia, Zoe, Gunnar, Mia, Nora, Chloe, Braylon, Katie, and Leah. Okay. Perfect. Alright, let's get Sophia, Cade, and Braylon up here. No, who was it? Just kidding. It was Leo and... Was it Braylon? Was it you or was it Kate? I think it was Kate. Huh? I know, I said Sophia. Sophia had the most. All right, so go ahead and exit out of that. I am now on to how to calculate net force. So I'm going to take it a step back here, and I'm going to zoom in really quick. So I have copied and pasted this website onto your announcement, okay? This website is here. It talks about how to find and how to calculate net forces using free body diagrams. Okay, so here's some examples. Here we have force, right? Tensile force and gravity. One is 1200, one is 800. Air resistance, we have 600, one is 800, okay? And then we have F normal force is 50, F of gravity 20. So what happens is, let me get my pen going here. When we have a free body diagram, which you guys drew yesterday, you worked on those free body diagrams that would have looked like this, right? And I want a color that's not, there we go. Can everybody see green? Is anybody? Okay. So what we have is every force is represented by a number in newtons, right? And usually, almost always, If the arrow is going down or to the left, it is assigned a negative number, okay? So for example, this right here, oh, is it not gonna let me? Come on. This right here will be assigned a negative number. F of gravity will be assigned a negative number. F of gravity will be assigned a negative, and F of friction will be assigned a negative number, okay? So it's already got its number. All we do is assign it a negative, okay? And what we do is we add all those numbers up and see what they equal. It's very easy, okay? So for example, when we're talking about F net of this first situation, we would have 1200 plus negative 800. So what would that be? In the first situation. So 1200 minus 800. 400, right? So we'd have 400 newtons. In which direction would the object be moving? Up. Thank you. Up. Why up? Why would the object be going up over down?
Because
1200 is greater than 800. Good. So this would be 400 newtons. Whatever this item is, this object, which we don't know because it's just represented by a box right now, would be going upward. Good. What about the second one? Negative 200. Good. So you'd have 600 plus negative 800. So we would have negative 200. Which direction? Down. Good. All right. Now on this one, right? You see how it goes, right? So we've got a negative here. We've got a negative here. Okay. So let me erase that real quick so it doesn't get confused. And you can see as we scroll down that all you're doing is you're figuring out, okay, we've got some negatives, we've got some positives, right? And so we now have to figure out if this one is negative and this is negative, right? So we have F net equals 50 plus negative 50 plus negative 20. You see that? So what's our answer there? Negative 20, and in which direction are we going? To the left. Good. To the left. Why are we going left? Does up and down cancel each other? Yes. You see that 50, positive 50, and negative 50 will cancel each other out. You add them together, you get 0, right? So the only force that is not counteracting anything, that has nothing to counteract it and nothing to oppose it, is friction. So since it's a negative 20 for friction, we are then going left. Left, okay? Does that make sense? So all we have is this 20. That's all we have is 20 here to go for friction, okay? And so if you see, really what we have is we just have that 20 for friction because these two cancel out, and so we're going 20 newtons to the left for force, all right? Even though, it's kind of confusing, right? Because even though this arrow is smaller than these two arrows, you see that? But these two cancel each other out because they are opposing forces. So all we have is 20 newtons to the left, okay? And so whatever item that is, whatever object that is, it could be a bird, it could be a dog, it could be a desk. That desk is going to go 20 newtons to the left, okay? Does that make sense? Yeah? Okay. And so there are a bunch, what I did for you, what?
I have a question. How do you get them to be negative? Like, why Why are they negative?
You assign them negative because they're opposing. So they're opposite, okay? So we can't add, since the arrows are going different directions, we can't add them together as positive numbers. Because one arrow's going up and one arrow's going down.
Oh, okay.
You see?
Yeah.
If both arrows were going up, we could add them together and both be positive.
Okay.
But see that one arrow's going up and one arrow's going down. So one of them has to be negative. Does that make sense?
Mm-hmm.
Yeah. So since we have one arrow up is 50, and then that's why usually any force assigned that's going up or right gets the positive. We leave it positive.
Okay.
Any force that's going down or to the left, we assign a negative value. Okay?
Yeah.
Now, that's not all the time. That is like 99% of the time. We'll assign it the negative. Okay?
Mm-hmm.
And I mean 99% of the time. Very rarely will you see the gravity be positive or the friction be positive. Very rarely. Okay? There are situations where that happens, but it doesn't happen often. Okay? So, I gave you this link because there are practice problems you can do down below. Okay? Down here, I give you the site here, physicsclassroom.com, gives you 4 practice scenarios here. Okay? And then you can see if you can get the answer right, and then it says see answer. So you know if your answer matches up with the answer on this website that you're doing it correctly. Okay? Does that make sense? So I've given you some practice problems to do if you're not doing the homework correctly. Now, the homework is calculating the net force. Very easy. It's the same situation. Okay? All I've done is, you notice what's similar from yesterday. What did I do? I just put it on the same pictures. Now all I've done is assign forces here, okay? That's all I've done. So you have literally 2 forces on number 1 to calculate, 2 forces on number 2. Then this is where it gets, notice I'm making it a little harder now, right? Now you have 4 forces, 4 forces, and 4 forces to calculate on the last 3. Okay, so I start easy, and then I make it harder as 1 through 5 comes along. You tell me, all you have to tell me is what's the overall net force and what direction is that object going? Which you should already know the overall direction the object's going from drawing the free body diagrams yesterday. Okay? Questions so far? No? Okay, so go ahead, get to work on this. Let me know if you need any help. I will gladly help you. Oh, and don't forget to show work. You have to show work for full credit. Yes, thank you. Please show work for full credit.